Section 8 here, we're going to get into shape of molecules. And I'll be honest, my high school chemistry teacher was miserable at this one. I just flat out did not understand. We had some ball and stick models, and we kind of worked with those. And he's like, see, there's the shape. And then we had a test, and we weren't given these, and we had to figure out the shape, and I just had no clue. I just flat out did not get it. In college, my professor didn't do a great job, but we had a lab where we actually played with these, and it kind of finally clicked for me, including the wedge dash notation. And that had never been explained to me. I was just kind of able to figure it out on my own. And so it's something that I was able to figure out, but I kind of taught it to myself. And I've since had other people come alongside me and show me better ways of teaching it. And so I hope that I do a good job of that here. But it is something that you really have to rely heavily on a table for unless you want to memorize this stuff. I'll point out here that these are all different representations of the same substance, methane. If you go back to the prior section, or maybe it's a couple sections ago, there's also a space filling version of methane that they had there. This here is what I would call the Lewis dot model, and then this is the Lewis structure or Lewis molecular model version of it. But you'll notice that both of those look flat and look to be at 90-degree angles. But in reality, the electrons on these things, they are negatively charged. And even though the hydrogen is attracting the carbon's electrons, the carbon is attracting hydrogen's electrons, you also have the electrons repelling one another, and you have the protons in the carbon and the hydrogen repelling one another. And so these things end up wanting to spread out. In reality, the furthest apart they can get is a 109-degree angle when you have four things bonded to a central atom. If you want to be picky, it's a 109.5, and I've learned that number to the point where I say it all the time. So if you hear me say 109.5, for our purposes, it's okay to round that down to 109. Yes, I know it's weird that we're rounding down, but anyway, there's a reason why we would choose to round down there. But it turns out it actually has this, what's called a tetrahedral shape. The tetra, you'll recall, means four, and you're looking at this and like, okay, maybe because there's four things on the outside, but there's actually five things there. Well, the tetrahedral is a geometry term, and it refers to the fact that there is a triangular face there, and there's actually four triangular faces on this thing. I'll try to draw each of them out here. And so there's three of them. Then there's this one down here underneath, and again, we're on a flat screen here, but you have to imagine that we are actually in 3D there. And then your fourth face is this one here. Unfortunately, the way I drew that one's actually the one that's in the back. But there are four triangular faces here on this. There's a triangular face at the bottom, and then three triangular faces here. Well, from there, we have what I would call a ball and stick model, showing the same thing, and that happens to be what this is their ball and stick molecular models. But drawing in 3D is difficult, and one way that we can kind of quickly note that is with something called a wedge and dash notation. Now, I've seen it done like this, although I'll be honest, most of the times I've seen it, the triangle here is turned around. And what they're doing is they're taking advantage of this principle that was discovered in art around the Renaissance, that if you have parallel lines, they don't actually seem to stay parallel, that if you look at parallel lines going away in the horizon, they actually appear to converge in the horizon. And so then that's what this wedge dash notation is trying to show, is that this hydrogen is actually coming out of the screen towards you, and this dash hydrogen is going back into the screen away from you. And it's part of why I put the green ones on here. If you imagine that we're drawing this on a piece of paper, if I just grab this one here, and we put these three, the carbon and the ones that we can, onto one plane, that is onto the piece of paper, well, then you'll notice that one sticks out and one goes back in. Well, then, because of this parallel lines converge thing, the dark wedge here is trying to show that it's sticking out, and then this one here, the way that I've seen it before, it will do the dashes with the long part of the triangle towards the carbon and the short part away from the carbon. So here we're saying that the hydrogen is closer and the carbon is farther away, but then here with the dashes with the wide side being at the carbon, taking this one and turning it around, we're saying that the carbon is closer to you than this hydrogen, and then we draw the other two in the plane as they are. I've even seen a lazy version of the wedge dash notation that does a dotted line and a bold line instead of actually taking the time to draw all the wedges. And I've even seen that done here on a 90-degree drawn model, just to emphasize that. Every model that we build is going to have some kind of limitation to it. Here it's the size of this bond here compared to the size of that bond there, the size of these two compared to one another. It's just, there's always going to be shortcomings to any way we draw these. But there are ways to nonetheless use what we have drawn to predict what the shape of a molecule will be. Anyway, that was a lot for an introduction, but getting into this. The thing that dictates shape is something called VSEPR theory, or valence shell electron pair repulsion theory. Basically, that electrons that are in the valence shell are going to repel one another, and they want to spread as far apart as possible around the central atom. There's an extra little bit to here that they kind of gloss over, and that is when you have something like the carbon with the hydrogens around it, it turns out that one does come out to be 109.5. The reason why we tend to round down is it turns out that when you have something like ammonia that has a pair of electrons here, well, because those electrons are unshared, those electrons are always around the nitrogen. And because they're always around the nitrogen, then sometimes when the shared electrons are around the hydrogens, well, then these electrons here will spread out a little bit more. And so they'll take up a little bit more space. And so if you imagine here, if we have this one be our ammonia and this up here is that pair of electrons, well, they spread out more. And in doing that, they repel, valence shell electron pair repulsion, they repel the others and bend them down some. And so we actually end up with an angle that's less than 109.5. Water molecules the same way. Oxygen there has two unshared pairs of electrons. It gets bent even more. And so we get an angle that's much less than 109.5 is usually how we'll describe that. And so it's why we tend to round the 109 down anyway, is because only a handful of molecules are actually the 109.5. Many of them, if they have those unshared pairs of electrons, start to bend that 109 angle and actually gets less than it anyway. And so, like I said, there's a reason why we round down. Anyway, the way that we determine shape, though, has to do with the number of groups around the central atom, the number of things that are bonded to the central atom. So here, we have two regions where things are bonded to the central atom, and the furthest apart that two things can get around a center is 180 degrees. And so then we end up with a linear molecule, and being a straight line, it's got a bond angle. We always measure the angle. You may recall from geometry somewhere that if we have angle ABC, that we have three pieces here that we can say angle ABC is equal to something, some number of degrees. Well, the bond angle is always between these things on the outside around the center atom. It's not this here is the straight line, it's the whole thing is a straight line, and we're measuring the bond angle between these things out on the extremities there. Anyway, 180 degrees. If we have three bonding regions, so something like this, where we have 1, 2, 3 things around that central carbon, well, then they're going to spread out to where they are trigonal planar. And so this would be an okay way to draw it. This here is a little bit more true to its real shape, but when you have 3 things, the furthest they can spread out is 120 degrees. Now, I've seen a lot of students want to call this 60 because they look at this and they see a triangle. And yeah, it kind of is a triangle there, but it's not the inside angles of the triangle we're measuring. Again, it's the angle between these things. It's these angles here, and you'll notice that's a circle. 3 parts of the circle, that's your 120 degrees there. In fact, if you want to think about this one here, it's one part and another part of a circle, 180 on each side. However, if one of those things, one of those 3 bonding regions is an unshared pair of electrons, well, then those electrons, they're not going to be part of that 120 degree angle there. Really, they stay there, they spread out. They actually squish this to be a little bit less than 120, but we end up with a shape that just has these 2 things around the central atom. And so this is no longer trigonal planar, which, by the way, means a triangle in a plane, in a flat sheet there. But we have something that we call bent. Now, it turns out that we have bent elsewhere as well. So this is a bent 120. There's also a bent 109, as we'll get to here in a moment. Getting back into the methane, it turns out that the furthest that 4 things can spread out around a central piece is 109. I've seen the math proof before. I've had a student challenge me and wanted to see it, and I can work through the math proof. I can dig it up if you want me to, but it's probably easier just to trust me that the furthest they can spread apart is a 109. Those of you who are live with me, I'll do a demo with balloons. Those of you who are not, I'll try to post a video of that anyway. I think it's really helpful to see why the 90-degree shape is not the furthest apart that they can get. And I think you can agree that, yeah, this here looks like it's bigger. It's the 109. It's got to be bigger there. But why is it 109 instead of 90? It can be a little bit hard to picture. And although mathematically provable, I think it's just much easier if you can see it done. That shape is called tetrahedral. Like I said, the tetra comes from the fact not that there's 4 things on it, but that there's 4 triangular faces on the molecule there. If we get rid of one of those, that is, if one of those becomes an unshared pair of electrons, then we just have the triangular-based pyramid here. It is a pyramid. It's a very low squat one, unlike your Egyptian pyramids, which are square-based, but a very low squat pyramid. And our bond angle in there is still 109 between those things, but we now have that unshared pair of electrons up top there, and so it doesn't get considered into what is the shape of the molecule. The shape of the molecule is the shape of the atom's arrangement compared to one another, and that one then is called trigonal pyramidal. You can hear within that, of course, triangle pyramid. As I said, there's another bent one when there's 2 unshared pairs of electrons around that central atom. Then we don't consider those when we're factoring in the shape of the molecule. We just consider the things that are left. And so this one here is also what we call a bent shape, but this is a bent 109 degrees. Now, by far, we spend most of our time in this region because of the octet rule, and octet being pairs of electrons. We spend most of our time in the 4 region here, where there are 4 electron groups, or what are sometimes called bonding regions. And is sometimes also called the steric number. But the bonding regions, the electron groups, the steric number, we spend most of our time in 4 because the octet rule will have 4 pairs. Of course, pairs are 2 and of electrons, and so then that's 8 electrons total, which is our octet. So we spend most of our time right there. However, if we have, as it mentioned there, double bonds in there, or if we have exceptions to the octet rule, those can also get in here, then we can end up with only 3 or 2 regions, and when that happens, we have different shapes. I will point out here that they mentioned the electron group geometry. That is, the electrons themselves stay tetrahedral here the whole time. That is, if this here is tetrahedral, those electrons on top of the ammonia or on top of the water here, those are still in a tetrahedral arrangement when they're considered along with the other atoms there. But the molecule itself, ignoring the lone electrons, the unpaired electrons, those then have these shapes. And by far, those are the most common shapes. If you get into a double bond, then you can end up in that bent or trigonal planar. And if you have 2 double bonds there, or again, exceptions to the octet rule, then you can end up in the linear region. So here we're asked to predict the shape of a few of these, and the simplest way to do this is by drawing the dot model first. So we start with sulfur here. Sulfur is going to be our central atom. It's the one that needs the most, and the hydrogens are never on the outside. But sulfur has 6 valence electrons. Hydrogens have 1, so it should be real clear and obvious that sulfur needs electrons here and here. And so that's where those hydrogens are going to get plugged in there and there. Well, now on the sulfur here, if I change highlighter here, there are 1, 2, 3, 4 regions. So we're into this area already for it, and there are 2 things bonded to it, and so there we go. 2 things bonded to it, 2 lone pairs. That means that our shape is bent and the angle is 109.5. And there I just said it, and as a side note, I highlighted the wrong thing there. I meant to catch my angle and not the example that they gave. Those on the right there are all examples. Over here, we're asked to do the same thing. So again, I think it's easier to do these as dot models first and then figure out the shape, I'm going to skip that one because it's the one we literally just did on the prior slide. And so PF3, so phosphorus has 5 valence electrons. You can see it's got a need for 3. Fluorine, it has 7 valence electrons. It has a need for 1. And I think you can see real quick that, okay, if phosphorus has a need for 3, here, here, and here, that's got to be where the fluorines are going to end up. And you're absolutely correct. And so we end up with the fluorine there, there, and there. And then all I have to do is put the lone pairs, the unshared pairs around the fluorines. I'm going to do the same for the carbon. One nice thing is because chlorine is in the same family as the fluorine, it also has 7 valence electrons. Carbon starts out with 4 valence electrons. I'm not going to take the time to do the highlighting thing here. I think you can see if we have 4 chlorines, they're going to end up on all the sides of the carbon. The chlorines, like fluorine, all have 7 valence electrons, so they're going to contribute 1 to be half of a shared pair, and then they each have 3 lone pairs, unbonded pairs, unshared pairs, whatever you want to call them, of electrons here. And now that we've done all those, well then here, starting with C, it's got 4 bonding regions, 4 electron groups. It's got 4 things bonded to it and no unshared pairs, no lone pairs. That puts us in this row right here, which means that this shape is tetrahedral. And the bond angle is 109 degrees. They didn't ask us bond angle, but you're going to be asked that at some point, so might as well practice it there. This one here, the phosphorus, has 4 bonding regions. It has 3 things bonded to it, and it has 1 unshared pair of electrons. So that puts us here on the chart, and that makes it a trigonal pyramidal with a bond angle of 109 degrees. And I will point out something that I mentioned that they say here is that the bond angles are approximate, and that's good enough for our purposes. Anyway, that finishes section 8.